into it and the person dies and just this orgasm world, like, ugh. He laughs at me.
Alrighty.
I'll start crying. We'll just like start laughing. Like, I'm crying right now. So frustrating. And I hate the season finale when it happens.
Okay. We'll get you guys started because I'm still trying to work out the logistics on next week's. You have 2 major events scheduled for next week. And no, it's not a birth of a child or a death of a person, right? It's going to be your lab test and your lecture test. And generally what I do is, because your lab test is not flexible, right? Other than you take it within those 2 days, right? Is I generally let students come up with their own solutions for the lecture tests, all right? So, and there isn't any right or wrong solution. It's just I say, propose to me what you would like, but it's staying on the schedule where it is, okay? Just so you know. So don't feel compelled to, come ask me, because it is. Now, as I reflect, and I haven't written this because, like I said, as in switching to OpenStax, I have to make some modifications of the things in the order, not the orders we do things in, but what's inclusive on each test, okay? And so, as I was reflecting on it, and I was thinking about what would be in the best interest of you guys for your lab preparation, is so for chapter 7 and 8, which I didn't lecture on, right? What I might do to reflect on that will simply ask you names of bones, or give you a feature from a bone and say, what bone would you find it in? So I might build into the test as I'm reflecting on this weekend, and I tweak your review, because your review is not correct right now for the lecture, right? I'll try to come up with a very good philosophy that helps you in lab as well, okay? Because we really do want to reinforce the material as much as possible in lecture and lab. And so, like I said, I didn't really talk about it because it was strictly, hey, name this bone, what's this feature, and so forth. So I'm not going to put pictures of the bones. That's something that you do in lab. But I might say, okay, tell me which bone has this feature, okay? And then for chapter 9, the joints are what you're covering. We'll just go into a little bit more detail on the joints, because in lab, they'll just say name it, right? Here, what type of joint is this, all right? So in lecture, there was a little bit more background, clearly, in chapter 9 that I'm going to utilize on your lecture test. So that won't be, a direct overlap between lecture and lab. And then chapter 10 that we're on now, we're going to have the way muscle works being the majority of the test. But, and that, again, that's going to be a bit of a challenge. So that won't be the majority of what you do in lab. The majority of lab time, you should be spending identifying these and thinking about what actions they do, right? And trying to keep them all straight in your heads. And again, even if you're one of those daydreamers, like I know some of you are, I see it in your faces every once in a while, right? When I'm talking, right? Unless I'm just not very excited. That's okay. You can tell me that too. But it's going to be a little bit more of a challenge again as you spend time in lab. You might not be on task, because I always say to my son, you're not really on task here, are you? Right? So you're going to have to make that extra time, and please do that for yourselves over the course of the next week, because a week from today you're going to have that lab practical, and it's not that it's hard, it's just so much information that if you haven't really prepared yourself for it and you haven't figured out a good strategy for how to keep it all straight in your head, you're going to be shooting yourself in the foot. And we see this all the time, unfortunately. We'd like the cycle to stop, right? Clearly, that would be nice, right? But it does take that extra, you got to be motivated to come in there and think about, what is it that I'm looking at, and why do I want to care about this? And, even if your motivation is, I just want a good grade, that's okay, right? Have that motivation. But it is, it is important that you can demonstrate those skills, that you can keep a lot of parts and things straight in your mind, because as you go on and you have to care for people and their lives are in your hands, it's nice that they have the confidence that you actually know the difference between a femur and humerus, right? So little things like that. So we're just, again, give you a warning here, and let me know. Like I said, I if it's something that you're going to need a test in a testing center, if you're going to need it on a Friday, next Friday, instead of in class on Thursday? Should we electrify on Thursday? That's fine. You have that to think about, and I'm trying to nudge you to think about it, okay? I don't need the answers right now. Just think about how you're going to manage next week, okay? So, and hopefully that didn't surprise everybody that you actually have a lab test and a lecture test next week. Because it would surprise you, well, okay, it's not a good surprise, but you still have a little over a week.
So is the lecture test on the same day, next Thursday?
It is right now scheduled for that. That's what I said. Because I won't finish this today, which means I'd have to talk more about it on Tuesday, and I really should talk more about it by Tuesday because it's a lot to swallow. I mean, there is a remote chance that I wouldn't even be done on Tuesday. But I'm going to tell you this. Even if I wasn't and we didn't actually schedule the test for Thursday, which it is right now, well, then I still got the problem. If you show up on Thursday, I'm not going to have your minds. You're going to be thinking about your lab practical, right? Your mind isn't going to be on this. So, we've got to be honest. So.
My lab's on Wednesdays.
No, Jane will be here. And Jane will be totally in the zone, all right? All right, so you've got a couple models, and you've got the big pictures with these mini men and torsos back there. So, look at them and think about this. Your challenge is I've got to find these parts, and I've got to keep them straight, so make sure you can. We will use both of these models on your practical next week, and we can ask anything about the A bands, the I bands, and so forth, and the sarcomere itself. So please keep it straight, all right? The myofilaments are evident on those two models, and they often are. One of them's on the practical, typically. That shows you just a sarcomere, and it shows you the troponin, the tropomyosin, myosin, and actin on it. All right. So, again, so this is a nice, cartoon for that idea. All right. So here, again, getting you ready for these events that are hard to see statically because they are very, very dynamic processes. Right? I just remind you again, you got to have electricity and chemistry working to trigger this response. And what you're going to want is if the muscle is to shorten, right, change its length, starting in the sarcomere and then billions of sarcomeres, actin and myosin are going to have to move. And specifically myosin, the M1 is for moving. It's the active protein, and then it will be moving the actin. And if this occurs, the sarcomere as a whole shortens. And of course, we also get this evidence from thinking about what a sarcomere looks like, that the sarcomere can only shorten so much. And that's what's nice about that model next door, not just because it's been made so that you can only slide it so far. The reality is you could only slide them so far. There are limits to the contractility of muscle. Okay? And so these actions that you're learning in lab are all related to these events we're looking at in lecture. Okay? That's really where we want to be, is what are we going to see. So this is, again, our overview. Let's see what happens in each one of these. Okay? Here's our neuromuscular junction. You don't see it on this model. You do on those two models. To remind you again and again, and then, like I said, when we go into nervous tissue, right, this is a motor neuron. So they don't even show you the end of the axon like they do on this model. Right? So, right, neuromuscular junction. This is coming very close to that muscle. The muscle does nothing without, right, this axon here from this cell, motor neuron, telling it. All right? Voluntary. So, how on earth am I sending the electricity and the chemistry down to this muscle? Okay, so when we say voluntary, you're choosing, right? You're telling. You are telling it, and you are aware. Let's take it one step further. You are aware that you're telling this. Now, you're not aware of the depolarization or repolarization, right? You're not aware of, like, the acetylcholine, but you have initiated, you've chosen to do this action. So, again, as we back up and talk more about the nervous system, we're going to say there's this big, huge area in our brains called the frontal lobe. Very big in humans, right? And we're going to say that all these, because the brain is just a bunch of these neurons, right? And the axons associated with them, right? Because we've just zoomed out. So your frontal lobe is from here on forward. And it's in this area of the brain that we're actually starting the whole process of contraction, up here. Right? As opposed to involuntary, when I call something involuntary, like what the heart does, and blood vessels, and the stomach, and breathing, diaphragm, then it's starting from the brain stem. Sometimes even the diencephalon, but the brain stem. If it's involuntary, the neurons that start the whole activity are coming from different areas of the brain. Yeah, Tanner?
What happens when you sleepwalk? Is that still voluntary?
Well, I would say that you're not consciously aware of it, but I would say it's still coming from the same region for control of those muscles. Mm-hmm. So I would say, if you ask it, though we won't cover it, that would be my simple answer to it. So you're not aware on that level, but you're still generating the action potential from the frontal lobe. Yeah.
Is the involuntary response, is that faster than voluntary response?
Not necessarily.
No? Okay.
So speed, it's a good question. Speed of transmission has to do with the size of the nerve itself and the types of connections. So just like I talked about the speed of contraction.
Yeah.
So actual reaction would be a combination of how fast can I move it based on size of fibers and how many fibers are devoted to it, and then what kind of muscle I'm making contact with.
Okay, so if you ever, could you have a faster response and just not have, or a faster
So
brain response?
I think your question is very valid from the point of we have these things called reflexes, which are generally done without our awareness, okay? And they would be considered voluntary. And I'm going to hesitate to say that sleepwalking is a reflex, right? But it could be, right? I'd really have to look at it, right? And they are there as retaining or maintaining homeostasis. So they tend to be faster only because they don't have to go all the way up to the brain.
Yeah.
They only have to go to the spinal cord because your control centers are your brain and your spinal cord. So in your spinal cord, as we get to the next chapters, right? So in this mass of tissue, or this mass that I put on here, it's bone, right, are a bunch of those neurons as well. And these neurons do connect to these skeletal muscles as well. And so the speed becomes very quick because I don't have to take it all the way up the cord. Because that's what your spinal cord is, isn't it? It's a big conduit moving up and down, right, let's take it back here, right, moving up and down this, carrying this information up to the brain. So we have to connect the dots, right? So what information? Well, the sensory, right? Because a reflex is always a response. Responses are always muscles and glands to some situation. Right? I'm not gonna, do anything to this. But I could punch him, right? And he might withdraw his arm, and he might do it without thinking, because most people do, right? I'm not really a violent person, I promise. Okay, don't ask my husband. Okay. So anyway, right. But you know what I'm saying? You touch things that are hot, you touch things that are sharp. Those are reflexes, and they move quickly because we don't have to be aware. We can generate a response without the brain interfering. Okay? But excellent questions, because we're going to get there in all cases. We won't talk about sleepwalking, Tanner, but right, we are going to talk about a lot of these things. So we have to get the players, right? We have to get the motor neurons. We said, yeah, here's our picture. They look like this. You can't see them with your eyes. You've looked at smears of the spinal cord when you did nervous tissue. So you saw a bunch of these guys, really big cells, all right? Motor neurons, we have a neuromuscular junction. So there, would you point to that for me, David? See the neuromuscular junction there? On the, would you mind doing that one? Right, so right here, right there, yeah. So neuromuscular junction, right back there, right? You got it, Elise? Ashley, excuse me, not Elise. I have Elise. Yes. So right there's our neuromuscular junction, and it's got a synapse. So the synapse is which part? Any guess?
The space in between.
Yeah. So it's orange on this, isn't it? I mean, color doesn't matter, but it's this dark orange here. So there's this little tiny space. That means they're two separate cells. They're very close together, two separate cells. So neuromuscular junction joining synapse there. Presynaptic terminal. Well, that means the end of the axon, doesn't it? Before the space. So, and we have to go through this because, like, when I write these words on a page, if you're not prepared for them, you're like, what are you talking about? No, seriously, you will be, right? Because presynaptic, what's that mean? You break it down, right? Presynaptic before the synapse. So this is the end of the axon. Postsynaptic membrane, what's that going to be? What's the postsynaptic? Who comes after this? Okay, we got that. So who is it? Who's the postsynaptic? We've got our presynaptic here. There's our synapse. So the end of the axon, the bulbs.
So everything that's...
Yeah, it's the muscle, right? The sarcolemma, isn't it? I mean, it's a white line on here, you know, but it's a sarcolemma, isn't it?
So it's the end.
Okay, so the postsynaptic membrane is the sarcolemma. It's the muscle's membrane, right? Right? Is that? I mean, because you look at words like this, you're like, what the heck are you talking about, right? But you want to make it simple and think, well, what is that? Because that's why lecture and lab work well together, right? Is that we say these words and you go and find them, right? So we got them in front of us, and we got to think about. So synaptic cleft, again, that's really that's the technical space, right? So the synapse is actually all of it together. So if you really want to be nitpicky, right? The cleft is really the orange here. Okay, so the synapse itself is this whole area. Okay, so I'm not going to be picky here, but we have to, again, if you read that, is that something different? Is that something new? Is it something important? Okay, so the cleft is really that space. So here on this cartoon, right here. So if we took and let's say you got the models in front of you. So here's right the presynaptic terminal, the end of the axon. Here's the postsynaptic, and they have nicely drawn in these sodium channels we were talking about last time. So this cleft is the space. It's the anatomical space. The vesicles, right, they're chemicals made by the axon, because we said this is an electrical chemical. And of course, these chemicals are always going to be acetylcholine. Oh, thank God, right? Because there are so many neurotransmitters. And this is easy. We want to start off with the easier stuff, right? And even in the context of class, we really won't talk much more about different chemicals than, right, norepinephrine and acetylcholine. But there are a lot of different possible chemicals. And that's what makes the nervous system complicated. The nervous system in itself is not a complex physiological thing. It really isn't. Because again, like I said with muscle, once you figure out what one does, you know what everybody else does. The difference comes about because you have 40-some different chemicals. But the honest truth is they're still only going to either stimulate the neuron or inhibit it. There isn't a lot of choice, is there? So where's the complexity? Well, you can have, hundreds of thousands of them, right, coming together. So in the end, what you do depends on the sum of all 100,000. And who else is talking? Who else is in the conversation? Right? So it's the numbers of connections that these neurons make with each other that really leads to complexity. Here, it's not. So we want to start with stuff and take that gift, right? Take it and say, because we're going to make it as easy as we can.
Where did you say that the synaptic vesicles were?
So they'd be inside the axon, right? And they're going to exocytose. Okay? Now, there's an event that causes this, and that event has to do with a change in the polarity of this membrane and a specific change in the movement of an ion as well. So in order to cause this event, because this doesn't happen just randomly, because this is going to be a powerful chemical signal. Just like hormones are just powerful chemical signals, right? That's going to be powerful. That has the potential to make some serious change here, okay? So, but to get this release, we do need other things to happen. And we'll kind of back up when we talk about the nervous system and tell you about that. But a real simple event is we'll say, well, when the action potential, which is the electrical way that the cells communicate, gets down to that axon, and it's at the end of the line, right? It's at the end of the line. We're at the terminus. We called it terminal. Well, if it gets down here, this electricity changes the permeability of this membrane, and a permeability just means what do you let pass? And it'll let calcium in. So now and for the rest of your life, as I said last time, know that sodium is high outside of a cell, and potassium is high inside a cell. Please also know that calcium is high outside of a cell. Okay? So when it gets down to the end, and this electrical events change the permeability of this membrane of the axon, calcium enters. And it's that event that causes this release. Okay, because you have to tell. Cells have to be told what to do. It's always through electricity chemistry. There isn't any way else, right? They don't have phones, devices, right? It's electrical chemical events. So now, this acetylcholine, very, very powerful, moves very quickly, because we were asking about speed, across this very, very small distance. And as long as there are receptors in the postsynaptic membrane, right, the sarcolemma, the acetylcholine will have an effect. If there are no receptors, there is no effect. So this is also a limitation to how neurotransmitters clearly can work. So even if we overcame the problem of a neuron making the compound and releasing the compound, we have to be talking to somebody, right? And that talking is through a receptor. So the postmembrane may not have a receptor. And that's abnormal, okay, right? But I said last time, you get situations like myasthenia gravis in which these receptors are destroyed over time by the person's own immune system, and it ends in paralysis. Because if you don't have receptors, the muscle's not going to do anything. It's waiting to be told. This is the message. Yeah, Kale?
Are there some nerves, or are all nerves at all in any way closer to like being measured with quantum mechanics versus like using your traditional, physics to measure like as far as transfer, how it moves, and this type of thing?
I have not seen any reports of that yet. Right. So acetylcholine, we're binding to a receptor, and this binding causes an event. So again, you're putting everything in order. That's what you want to do, and you want to do that. Believe me, you're going to do that for all mechanisms that you talk about in the body. Because when you try to treat a disorder, which is always what they're going to have in common is there a problem with homeostasis, right? I said, but in treating that, you have to know where there was a problem. Right? So we couldn't give somebody with myasthenia gravis, I mean, we could, and when we do, but we couldn't just keep giving them more and more acetylcholine because there's no receptor, right? I mean, we can try to get whatever receptors they have, but in time, they're going to lose all the receptors, so you could give them acetylcholine all day long, and there's not going to be any response, right? So you see what I'm saying? It's like you have to be aware of what the relationship of the events are to try to figure out how to help somebody. Right? As we look at a disease like Parkinson's, and there's lots of neurodegenerative diseases, aren't there? Well, one of the things we realize is that the cells that make dopamine, another neurotransmitter, are dying through time. And so one of the very, somewhat successful strategies for treating people with Parkinson's is just give them dopamine. Because they're just not making it anymore. But that's not clearly going to work in this. It's not the problem isn't making acetylcholine, it's responding to acetylcholine. Okay, so that's just to give you this idea that disease starts to be pretty. You have to understand relationships, or you're forever doomed in just repeating a useless therapy.
So I read a report that was talking about people with Parkinson's, and it talked about how marijuana would help it. But how does that work from like a physiological?
It probably relaxes some of the spasms. That's my guess. I'd have to look specifically at that. But it probably affects the outside the brain stuff. But that's a guess. It's a guess. Okay. So again, when we talk about pain and all the different ways we can manage pain, because that's the biggest deal in medicine right now, is medicine is very imperfect. I mean, terrifically imperfect. I think most people don't realize how imperfect it is, honestly, and very expensive and imperfect. But it's what we have, right? And the vast majority of what clinicians end up doing is really treating pain. And so the good news is that we have lots of different ways we can treat pain. It doesn't have to be just opioids. That was just a bunch of lazy clinicians who were wrong and created a crisis now with it. Yeah. So there are many ways to deal with pain. So, but that's the good news again, and it all comes down to with that is it's blocking a pathway, blocking the transmission of this electricity, and you block the effect the electricity is going to have. So that's why we're going to say in chapter 11, 12, whatever, I'll say, hey, when your mom said stand up and shake that off or rub that off, right? She wasn't lying. right? Because you can, right, minimize pain by doing rubbing. And you can minimize pain by thinking. It's just unfortunately people with chronic pain, sometimes you can't think anymore because it hurts so much.
With the opiates, isn't it like it blocks the pain receptors to your brain or something?
Well, technically you can't perceive pain in the brain itself. The pain is out here. It's in the periphery. It's not a central nervous system. So they're preventing the transmission, all right, of these neurotransmitters, all right, that result in exciting an area of the brain that then tells you you have pain. So the brain's telling you that, the brain isn't actually sensing, is what I'm saying, okay? So, and so the trick is, I just gotta tell the brain some other reality, right? And drugs work very well at telling the brain another reality, right? But I'm just telling you, there's all kinds of different ways. I mean, this is why we don't fully understand, you know, acupressure and acupuncture. They are legitimate therapies for pain management. You just gotta have somebody with experience that really understands, you know, where are they affecting, and that's harder to come by. Yeah, Tanner.
What about like a headache? Is that like legit pain in the brain?
Okay, it's a pain in the brain. It is a pain that's caused from the vascularity, not the brain tissue itself again. Okay, and it's still chemistry. It's still just chemicals being released. Oftentimes you realize too, it can be just simple things like low oxygen. That's what causes angina in the heart. Which is pain. So it's an interesting thing. And like I said, there's lots of good conversations, but unfortunately we have to get back to this conversation. So we have to, again, let's just get how these nerves talk to these muscles, and then I love the fact that you guys are involved, because this is the part that's really fun. But I won't have all the answers by any means, right? But it's also very, very important, because like I said, I'm not kidding. When I first got into the basic research side of medicine, which is where I've been pretty much most of my life, except when I started teaching, we were talking about pain management, and we're not going to stop talking about pain, because it's tough. And you get a lot of people in chronic pain that we can't solve their problems, but we got to figure out how to give them quality of life, don't we?
Yeah, so you're stuck in the complex.
Yeah. All right, so back to our motor unit. We've already said this too. I said the motor unit really is all the muscle cells that, right, axon is talking to at the same time. So, because we put them as unit because they're all going to respond to this nervous tissue. Because, right, muscle is the responders. They're going to respond to what they're being told. And they're all going to respond if they're being told at the same time, aren't they? So it's a motor unit. Motor, again, for movement and unit. And this can vary from just 2 or so muscle fibers to thousands. Because I said this is your difference between fine motor movement and fine control and gross motor movement. That are very important terms when we talk about like occupational therapies and physical therapies. All right, so here's the like pages of these unfun terms right now, right? So we got our vocabulary, so now we have to like figure out how this happens. So the term we use for this is excitation contraction. So again, excitation, excitability, we talked about, that's going to come down to the electrical chemical. All right? Contraction is what I'm after. So this is really appropriately showing, here's this causing this. Because again, I'm going to tell you once and not the last time, one more time and not the last time, that yes, muscle cells are not going to do anything if they can't hear the nervous system, right? If the nervous system is not telling them. So, it turns out that a lot of your cells, arguably all, have this membrane potential. This is what we were talking about last time when we said, because of these, not alleles like I've written up here, because of this difference, I told you guys, in these ions, right? And there's a little bit out here, there's a little bit in here. All right, because of this difference in ions, and we could put calcium and smalloon and magnesium and chlorides and phosphates and sulfates, and there's all kinds of stuff in these solutions inside the cell and outside the cell. All right, but ultimately this difference, not having the same and the same numbers, results in a charge at the membrane, which we always report as a negative. And it's as though we stuck a probe, some way to measure this, right? So let's say there's our probe. We stuck it in the membrane, and the probe is measuring this comparison right across this membrane. And so it turns out this is our situation. We said at rest, doing nothing, because of these distribution differences in ions, it would be slightly positive outside and slightly negative inside. And this just varies throughout the body. There's a difference, there's a range. So it says again, muscle and nerve, because we're not going to actually excite epithelial and connective, but muscle and nerve will generate their own electrical signals called action potentials. So here's where we vary. That's why they're called excitable. That they can take and change this arrangement of ions and therefore change this arrangement of charge, right? And if I do that, it's an action potential. So potential, again, is paying homage to the possibility, right? If you have potential, you're not doing it now, but you could do it. So that's what we call, again, resting membrane, not doing anything, resting potential. And that would be that number minus 60 to minus 90, depending on the cell. And then an action potential, action, right? This means we're directing it to that you're doing something, right? So muscle and nerve can make changes in ions which result in, right, causing this thing we call an action potential. We also casually call this a nerve impulse. If you've heard that term, we kind of use those interchangeably. And that's what I'm saying here, right? You're going to control the movement of the ions across the membrane, and this will create current. So as we've mentioned several times, and I'm just saying it formally here, right? That to get that contraction, to get that muscle to shorten, the sarcomere to shorten, I'm going to need stimulation. And that stimulation has to produce an action potential. So it's not just, I don't just stimulate it and I automatically get an action potential. It has, there's steps. And I say in skeletal muscle, this always starts with the nervous system. In cardiac, it doesn't. In smooth muscle, it doesn't always start with the nervous system. Okay, so that's why we say it here. But we're not talking about the cardiac and the smooth right now. All right, so that's our, again, this is defining and thinking. All right? So how do we get there? We've said this a couple times. Again, acetylcholine. So here's again, same cartoon. Acetylcholine is key to this. So I give you steps. Steps you should memorize, for lack of a better term right now. Hopefully they become very, you know. All right, and I'll have a question on the test that says put the following in the right order. I'm warning you right now. Okay, there'll be 6 steps, and I'll say put them in the right order. 6 or so. So if we start with, and please again, we'll back up and we'll talk more about the action potential that this neuron actually generated. But right now, there's an action potential that's coming down. That's why they show you this kind of lightning bolt looking thing, right? And that is resulting in this event. The vesicle's moving, the vesicle's fusing, right? So exocytosing their acetylcholine. It moves across very quickly. So that's got to be step 1. We've got to give it to acetylcholine. All right? And then we realize that when it does this, so here's a closed channel, there's an open channel. Closed. When this acetylcholine binds to its receptor, this event happens, right? Sodium channels open. And because we realized and understood this before, or at rest, before this action potential came down the axon, we realized that opening a channel is going to mean sodium moves in. And we said because sodium is positive, the inside of the membrane is going to become less negative. It's taking its little positive charge in there, right? And that event is called depolarization for that reason. We are lessening the charge difference, the polarity. Okay, so more sodium on the outside, inside the cell is more negative. Right? You should be able to predict this. All right? Now, there's a lot of good ones. Let's see if it still works. I thought I checked it, but let's see. Because it's cool to see this stuff in action. And I think our sound, no. I did take these, I checked this again, when I made these over the summer, it was working. I have other YouTube videos for you guys, I promise, and you can find more if you like, but there should be some in Canvas and I'll check it out. This is I really like this cartoon because it really shows you the connection between, here's our sarcolemma and here's the T-tubule coming in, it's just imagination. That's why I said pay attention to the fact that you got all these little dimply looking things here, that's the entrance to a T-tubule, right? Which is simply shown in orange, then on that one it's yellow on this one. But you see, this is entering. So what does this mean? It means I can carry this change in charge into the cell. It's not just going to stay here at the membrane. All right? So there's no axon here. So we had to have that event with the axon. It had to be there, and it had to release it and so we call this a local, right? Because it's just a one out of many, right? Lots of space on here. So this is a localized change that occurs first, right? And so we often do say that these receptors, or the sodium channels are gated. Sometimes we use the term gate, but the sodium channels are ligand gated. A ligand is acetylcholine, it's a chemical, okay? And once they open, because again, the ligand gated means that's the trigger for them, that acetylcholine is a trigger. Once they open, their change in charge, which is only happening right here, only here localized, will trigger voltage gated sodium channels along here. So this event leads to another event. And again, I just bring that up. I'm not going to use ligand and voltage gated to try to get you to discriminate that, but there are different types of sodium channels or gates. Okay? Yeah, Cam?
Do sarcolemmas always stay the same throughout your life, or can they increase the amount of pores that occur, the size?
It's a good question. I would venture that they probably could, but I don't know that with certainty. I'd have to look. Right? So could they become more sensitive or better? I would venture that they could, but that's, again, because it wouldn't take a whole lot of things to change to get that to happen. So, all right, so again, we're going to get this change here at the synapse, right, at the junction, and it's going to cause a change, cause and effect. It's going to spread this change in, right, ions to the next area of the membrane, and the next, and the next, and the next. So it's a cause and effect all along here. Well, eventually, I'm going to get to one of these, aren't I? And this is just where the membrane goes in. So the electrical changes that began because of acetylcholine are going to, what we say, propagate. So they're going to move along the membrane itself, the sarcolemma, and then they're going to enter. So it's very important I get that. They're going to enter into the cell. Because this is just the membrane as well. And now I'm changing all these channels along here. Okay, so travels along the sarcolemma, and it will enter a T-tubule. So cause and effect. When I change the polarity of this membrane here, well, it's next to another membrane, the sarcoplasmic reticulum's membrane, which is also polarized, right? And so this change here causes this one to change. And again, the take-home message is, now it's calcium. So I must understand as I'm looking at these models of muscles here, whether it's the white, right, sarcoplasmic reticulum, or the yellow one on this one, inside these tubes is a whole lot of calcium and very little outside. We are intentionally keeping it separate compartments. So this event, depolarizing, right, the T-tubule is going to cause this one voltage-gated calcium channels to open here. And because it's high in here and it's low out here, calcium's leaving and moving out into that sarcoplasm, all that cytoplasm. So that it wasn't there before. So this is brand new. Now calcium suddenly, a lot, is out here. And what else is out here? Well, the actin, the myosin, right? The troponin, the tropomyosin. And hopefully you all remember troponin from last time, because that's a protein that calcium can bind to. So you did learn something. All right. So you see where we're leading? We're getting all these cause and effect. This happens, it causes this happens, and so forth. All right? So, right? And again, don't ever fail to back up so you're not forgetting as we really focus in on the event, you're forgetting how they all tie together. So again, excitation, contraction, you got action potential came down, right? Changed the membrane of the axon, the presynaptic terminal, releases acetylcholine, binds to its receptors, opens its sodium channels, and then it spreads. See, so it's got nicely here, it's spreading along, goes into a T tubule. This change in electricity in this membrane triggers an event in that membrane, which we already decided is calcium channel. Calcium's now released. So it's an excellent, excellent cartoon for that. Calcium's out. All right? So this calcium will quickly diffuse, right, from where it's high to where it's low. And that means it's going to start to bind troponin. Right? When troponin, this little one along here, with its binding sites, binds this calcium, when they can get together, and they only can get together because of this event, which happened because of this event, which happened because of this event, right? When they can, and they bind, it moves tropomyosin, this long rope-like protein. And that's important because tropomyosin was blocking actin's binding site for myosin. So without this calcium, you couldn't get actin and myosin together. And if they don't get together, you can't contract. Okay, so again, it's just a very simple cause and effect. It's really not hard. So see how we're talking about words that you're not used to, right? Yeah, but it's not a hard event. It's a really good place for us to start in A&P1. And so if I've lost you by this time, it's okay. It's fine to check out while we're talking together here. But don't stay, right? Come back to this again and again. And think about it in your own terms when your brain is ready to think about it. Because you have to think about it. If you want to understand, you want to help people, you got to understand how they work. Right? So we're going to get this event, aren't we, from all this? We're going to get myosin heads binding to actin. But all this had to happen before I could get there. Right? And if they can bind, then myosin can move. That's what that little arrow shows. It can move the actin. And so the actin's attached again. If you want to picture this room as a sarcomere, right? And we have this actin attached to these Z lines. Well, this myosin in the middle would start to pull them on both sides, right? Pulling it like this. Pulling both walls simultaneously together. Kind of like that scene in Star Wars, right? In the garbage disposal. 1977, too long ago for you guys? Right, so, yeah. All right? Famous scene, come on. All right, so, anyway. But in you, instead of nearly being crushed to death, but rescued in the end by C-3PO, right? You, right? Well, and R2-D2, right? Yeah. We have to about C. All right, so, and you get all these sarcomere shortening, which means you get this visible shortening of the muscle, which we call contraction. And then, depending on the way that muscle moved, you either get flexion, or you get extension, or you get abduction, or adduction, or rotation. Right? All those lovely terms we came up with in chapter 9. All right. Yes, all good things must come to an end when it comes to skeletal muscles. We talked about even if you didn't want to, fatigue, which I did. So you're going to relax. Well, if I want to relax, which see, here we got the muscle, right? So I can shorten and relax, and I can do this very quickly, can't I? Over and over again. That's what's so cool. But if I want to relax, which is where I want to be here, right? The muscle has lengthened again, right? Well, I've got to get the myosin off the actin. I really have to get the calcium back into the sarcoplasmic reticulum. And I've got to stop sending acetylcholine. And one more thing. I've got to destroy the acetylcholine that's still there. So sometimes, because we know these powerful effects of neurotransmitters, we manipulate this as well, don't we? We manipulate how long a neurotransmitter is in and around the other neuron or the muscle. What is a classic one? Because I always have to give you guys things that, I'm not saying you personally relate to this. I don't care. I mean, I really, you don't have to tell me that. That's personal information. But in thinking about this, one of the most commonly prescribed medications manipulates the presence of the neurotransmitter here. That's what we use for depression, isn't it? We call them selective serotonin reuptake inhibitors. What does that mean? Serotonin is a neurotransmitter, and we're choosing to leave it there, out in the cleft. Why are we doing that? Because serotonin, to some extent, is your happy neurotransmitter. And if it's around longer, you're not depressed as much. All right?
Burn it out.
So, except medicine's not perfect, right?
Yeah.
So in this circumstance, so you have a couple choices here. But I need you to understand, this is the message, so I have to destroy the message. All right? If I want to stop the contraction, I really have to destroy the message. And so I got a couple choices, and I just gave you with serotonin. I could prevent it from returning, because a lot of neurotransmitters are just returned back to either the axon itself, or they are returned back to a neuroglial cell, a support cell. Because some of the neuroglial cells actually make the neurotransmitters, but they can store them for sure. So I'll be with you in just a second, Kale. Here, it's not the reuptake we actually do. We actually destroy the acetylcholine. So it is, right, destroyed if we want to get relaxation. Because remember, it's the message. It's the important message. So we have an enzyme called acetylcholinesterase. And it is going to destroy this. Now, it's not obliterated, because matter isn't created or destroyed. It's just taken apart. The cell will take back up the pieces, and it can reassemble it. But you do have to destroy the message. And the destruction of that will allow the pumping. So that's why I said you have to have ATP to relax as well. Pumping of calcium back into here. And it has to be pumped because it's still usually higher in here than it is out here, in spite of the fact that you release some. What was your question, Cam?
So how does it go back? I was doing my
Endocytosis.
Well, I mean,
You
yeah, but
trigger it?
isn't the nerve response, isn't the nerve like the system of the nerve?
Well, the nerve again is responding to electricity,
It
so.
always goes the same direction, right? And you just keep proceeding, and then it
Well, no.
proceeds and comes back down.
No, there's some safeguards to try to keep it going in the same direction, but not necessarily.
Yeah.
All right.
Well,
So yeah, so you're changing the voltage here, and that's going to let it go back. All right. Okay. So we're just going to reverse everything too. Once the calcium's not around, right? The troponin releases it. It changes its position. The tropomyosin shifts back and covers. So I want to, like I said, I want to do my contraction. All right. So if I look at this, if I look at what's happening then, just from the perspective of the sarcomere, here's what it looks like. And here's often what you're going to see when you focus in on an animation, right? That the myosin with all of its heads, right? So this is a relaxed. Everybody should get that, right? Because myosin is not touching actin. And in fact, myosin can't. Because this tropomyosin is blocking the site. It can't. So that is a relaxed muscle. And so here again, they're giving you the parts. This, of course, would be your A band. These would be I bands, right? There's your H zone, okay? So just to put us all in perspective, because there is differences in this when we contract, all right? So I go through that. Acetylcholine is released, right? So between here and here, what had to happen? Acetylcholine had to be released. It had to diffuse across the synapse. It had to bind to its receptors. It had to open a sodium channel. And that sodium channel would have depolarized the membrane, the sarcolemma, right in that area, which would then cause, right, the other sodium channels around it to start to depolarize. That change in polarity would move then along the sarcolemma until it reached the T-tubule. It would move, the changes would move into it, right, depolarizing that membrane, which would cause the sarcoplasmic reticulum to open its calcium, its voltage-gated calcium channels. Calcium would leave the sarcoplasmic reticulum, it would come out here in the sarcoplasm. It would bind to the troponin. This would shift the tropomyosin, and then we get this. So all of that had to happen between here and here, right? And that's what we need to be aware of. And at that point, myosin could bind to actin. And this rightfully shows you that not all the myosin is binding at this time. And so what we're going to see is it's going to bind, and the binding's not enough. The binding will be the start of contraction. But we said there's also isometric contractions and isotonic contractions, and some variety in a way in our contraction. Okay? So binding will generate force, and that's what we're after. Force. Right? Some amount of effort, some amount that will counter other forces, like gravity. Right? And then, if we continue on, we could move the myosin head, because I said this is the myosin's where the ATP is going to bind. And myosin's what's actually is changing. And as it's attached here and it moves, it'll move the actin, right? Pulling it inwards towards this M line. There is a point, though, I can't continue the contraction into there. I'm fully contracted here at this point, aren't I? Because I don't have any more overlap I can do with the actin. I mean, they've hit their limits, haven't they? Right? I can't really shorten this sarcomere anymore, can I? And when I have, right, of course, if I shorten the sarcomere, I lose my H zone. That's gone. Right? It is the M line. I lose my I bands. And I still keep, and will always keep my A band. My A band is always going to be there. Yeah, Tanner?
What happens when you cramp?
When you cramp, it's a sustained. Cramping, there's a lot of things that can cause cramping, but usually it's when you talk about pains and changes, I say to students, okay, it's circulatory, or it's cardiovascular, or it's neural in its nature. So you could have undergone such a sustained contraction that it's an ionic imbalance. That's one possibility there. But yeah, it's more or less a sustained, and you're trying to keep it, and you're experiencing pain because there's such a change in the balance of ions. That's a really simple answer. All right. So, and again, calcium leaving. So we have finite. So again, carrying that question through, we have finite levels of all of these, right?
So is that why they tell you to eat a banana or something?
Well, they do, but it's not going to be like that, right? I mean, that's the whole thing. I mean, we say a lot of things, and honestly, the short answer again to that is that, look, we know that there's a placebo effect for a lot of things. So yeah, if you believe it will, right, there's a chance. I wouldn't say a good chance, but there's a chance that it will. But yeah, the idea is against bananas have particularly rich in potassium. Maybe that's the cause. Maybe you haven't taken enough calcium. I mean, it's just there's a lot of different ideas. Harder to show in research, but there's a lot of ideas, and that's again, it shows people are thinking. Again, as long as it's not a cramping of your heart, you're probably not going to die from it either. So that's always nice. So, but again, in the heart situation, it is an ionic imbalance. I mean, that's exactly what a heart would be. All right. So, all right. Again, you want to be able to walk through this and think about this, whether it's going back through the book and reading the notes, or it's thinking about it from an animation. All right. So here, when we really focus in on what's happening between myosin and actin, because that's all we've done here, is we just kind of complete this idea of the ATP, which we want you to have. We have to get down to molecular levels. We have to understand the body operates on the level of molecules. So here is we're just looking at one specific relationship. Understanding, again, there's lots and lots. Lots and lots of myosin heads possible. And of course, the more myosin heads I have and the more actin I have, the more force I can generate, which is exactly the way weightlifting works, isn't it? I don't add more muscle cells because hyperplasia is not something that skeletal muscle cells do. I add more actin and myosin because the more actin and myosin I have within a cell, the more of this contact can be made, And with each contact, I generate more force. But of course, we all have limits to that force because of for this very same reason. Different size muscles, different amounts, and we'll take it a step further and say, well, different types of contractile fibers, which all comes down to myosin. When we talk about slow oxidative, fast glycolytic, it's all myosin. But we just, because it really isn't a paradigm shift in the way you think. Honestly, it's not. It's not like some of the magic we try to throw in quantum physics, which is, to some extent, a problem in quantum physics, right? Is that there's so many things we can't see, and tests for them are so we're just not there, that this becomes a harder field to wrap your minds around. But just because you can't see it, this is a very straightforward relationship we're talking about here. Okay? So here's what I need, right? I got a bind. We already figured that out. We figured out how we got that binding. Again, by moving tropomyosin, which happened because troponin binds calcium, and calcium was released because you work backwards if you need to, right? Over and over again if you take that, right? But it's going to then pull. It's going to come off. This is myosin. It's going to reposition, and it's going to attach and pull and come off and reposition. So, and it'll do that until we run out. As we showed you last one, we can hit when we are fully contracted. We're fully contracted. There isn't any more opportunity. You can't go any further, right? So, right? I say here for the pull, and that's what your cartoon shows you. So, myosin's got these binding sites, right? And so, at this point, ATP has been broken down. It's come apart. We have the little I means inorganic phosphate, and associated with this adenosine diphosphate. So they're very, very close together, and we are going to have to reform ATP, because I said this requires ATP. So here it is attached, and here's these molecules associated with it. Well, when it pulls, which we do refer to as a power stroke, when it pulls, changes that position, see, that's what's changing here, and this changing pulls the actin, because it's attachment. So let me walk it through now. Right? These molecules come off, and they reform very quickly and reattach. Okay? So the reattachment of the ATP allows the myosin to come off. We said detach. And it'll reposition itself back to this. That's the, recocking, if you will, or repositioning. And then it can attach again. But this time, understand, it's going to attach at a different place, isn't it, on the actin? And then it can repeat it again. As long as there's calcium to keep that troponin and tropomyosin off the site, as long as there's calcium, and as long as there's ATP, I can keep doing this. Again, to the point where I can have, I've just shortened the sarcomere as much as it can be. But as long as I keep calcium and ATP, I can hold that contraction, right? I can stay flexed. And you do this in a lot of your muscles, don't you? You hold the contraction. When you sit upright and keep your head upright, that's a sustained contraction for long periods of time. So that's the kind of things you want to relate to when trying to understand this. All right? So I'm just walking you through this idea. Moves it towards the M line, power stroke. Myosin is now in its low energy state. It comes off, right? And ATP attaches. And if that's not available, the myosin doesn't detach. So here's what I was talking about with something like rigor mortis. Because when you die, your mitochondria aren't going to keep making ATP, right? And so you would stay in this position, right? And then enzymes and bacteria would degrade this connection, and that's why you relax after about 24 or 48 hours. Yeah, Kim?
So, two things. One, why does it go back into, what makes it go back into its position?
Okay, it's ATP is literally pushing it.
Well,
So this pushing, coming apart and binding changes the positions or the shapes of proteins.
What makes
So
ATP
when it falls apart, it's again, ATP is pushing or changing the shape of the protein itself, myosin.
Yeah.
Okay, so that's what you're going to see. ATP's job as a small molecule is it gets lots of places. That's why it's our currency, and it falls apart easily, which is also very valuable for us for energy release.
ATP
right?
doesn't just do anything because it has usually has an enzyme, but is there just something what's making the ATP do that?
Well, the enzyme will put it back together, all right. But falling apart can be a spontaneous
Okay, that's
reaction.
what I'm saying, like, why,
Because this is not a stable molecule. That's what why I made a big point of saying that to you guys.
Well, that's
ATP
maybe-
is not stable.
the
Putting it back
last
together is
one.
definitely, you have to have kinases to put phosphates back onto things, okay? And ultimately, that's what happens, of course, in the mitochondria with the synthase. But here, when molecules fall apart, they can do that spontaneously because they're just not stable. Some stable relationships. Those are laws of physics. All right, so
How does steroids work?
So how do steroids fit in here? Well, steroids are going to actually affect the genetic information in a nucleus, something like this here, okay? Which is going to tell the nucleus to make more actin-myosin, okay? And again, you understand that if you run out of calcium or you don't take in enough calories for ATP, that's not going to matter anyway. But they're going to manipulate the building materials in a muscle. Frankly, that's steroids are powerful because they tend to go many places in the body. They enter into cells because they're lipid soluble, they're lipid based, and they are powerful, again, chemical messengers. So it's like an acetylcholine, again, very powerful acetylcholine that's able to go many places, not just across this short distance and then it's destroyed. Okay. So ATPase again converts the ATP to ADP again, so there's the enzyme you wanted there. It recox, energy released by this conversion will change it. So again, you're really talking about this movement of this. It now attaches at a different site, as we said, and this will move it. So as long as there's acetylcholine, calcium, and ATP, the cycle of cross bridge will occur. All right, so over and over again, I just have to have the right ingredients. They liken it to rowing a boat. I've always likened it to ratcheting, but it doesn't matter. It's an analogy, whatever analogy, metaphor, you guys like. But it'll keep doing this until it runs out. So calcium's got to be around. Acetylcholine keeps needing to be sent, right? And I just constantly reform that ATP, if I can. Again, because I still, again, have to have energy available to put that phosphate back on. Right? All right, so here's giving you again this idea that there's a limit going from relaxed to fully contracted, that there's a point which you're not going to get any more binding between actin and myosin. And that's the point where, if you're trying to move something that's really heavy, well, you've taken up all these binding points. There's nothing left. You can't generate any more force. The force you have won't overcome the force of the mass of this thing and gravity's effect on it. So you're not going to move it, right? So that's why I said when you do weightlifting, then you challenge that, and in that process, if you added steroids, right, you would produce more actin and myosin, and they would contribute to allowing you to have more binding potential, which meant more force. Or you could do it again. You just challenge your muscle. It's just steroids tend to do this a little faster, and of course you make your own steroids as well too that contribute to this. So, all right. So how many myofibrils will participate and how far will they slide? That's really the question I'm getting at here. So how many of these do you have in a muscle? And like I said, clearly these larger muscles in your lower limbs have a lot, right? Compared to much smaller muscles in the upper part of the body. But that's from a lifetime of use, just like we talked about. And that's what creates these differences in the bones. to which these muscles are attaching. All right, so that's trying to connect those concepts together. That, again, this heavier bone supports a very active muscle that's generating a whole lot more force. And when it generates that force, the pull on the tendon will actually change the bone. And when the bone changes, of course, what it's doing is it's reinforcing the anchoring. Right? So it's really a nice relationship that we simply sum up and say that's adaptation. Right? You change to suit the world you live in.
So this happens like every muscle, even when you blink or like smile?
Yeah, I mean, yeah, but now when you blink and smile, you're not really have to overcome much force. Right? See, that's the real problem. That's why I said I can move my arms all day long, but they don't work constantly against the force of my legs, which are supporting everything else up and the effect of gravity coming down. So it's really, that's what it comes down to, Tanner. So it's how much of a force do you really have to generate on how much and how often do you have to generate it? So I say here again, the number of muscle fibers is genetic, so we do inherit that. But strength, so again, number of cells, but the cells can change in the amount of actin and myosin. So you have a genetic predisposition, but it's not the end of the line. You can't say, well, I had this really small parent, so I'm going to say it's not the way it works, right? Because you can adapt by adding more actin and myosin, and troponin and tropomyosin, and so forth, okay? So strength is dependent on the myofibrils and the sarcomeres, and they can change. And that's what we just want to bear in mind as we talk about this. So energy sources, all right? Because calcium, really, we've covered some of calcium already, haven't we? We said in chapter 6 that if your blood calcium levels are low, well, you've got hormones that are going and they're going to tap this wealth of calcium, aren't they? All kinds of calcium in these bones. So I could probably cover my calcium needs. Now, I may not cover them fast enough in a situation like a cramp, but I probably, to a point, can cover my calcium needs. My energy is a different story, isn't it? Because energy isn't as immediate, well, and neither is calcium, by the way, but it's not, it's coming always from an outside source. Oh, I can store it, right? I can put it away as fat. I can put it away as glycogen, and muscles are very good at glycogen because it is so active. It has adaptations to suit its needs. That's what's really wonderful about this, right? But I have to get to ATP. I have to get this, and ATP is most efficiently made by mitochondria, which we talked about last time, which is why muscle cells have a lot of mitochondria. And I said, again, a heart muscle would have 10 times more. Because having the right organelle to do the energy transfers is really important to keeping up with your energy needs. Right? So muscle is well suited to maintain its energy needs because it does have a lot of mitochondria. Right? And then there's a few other things we want to look at. Okay? And that's all I'm saying here. That's the first part. So, storage is very low, as Kale was asking. It's an unstable molecule. We're not going to store energy in ATP for long term, which is why, poisons that uncouple the transfer of electrons and the electron transport chain tend to kill you very, very quickly. Because you uncouple that, and you can't make ATP in that last step. There. Okay? So, I'm not going to do that. But I want, again, a way to quickly get ATP because I don't want to have to wait to generate enough ATP that I can form the cross bridges again and move, right, do the contraction. And I also realized, too, that I can't relax either without ATP. So even if I didn't care about moving, I can't shorten or lengthen without ATP, all right? So I probably am going to need some other way to get ATP. Now, I want to put this in context. We didn't have to talk about this in epithelial or in bone because while they still needed ATP and ATP ruled their synthesis reactions, if you did run out of ATP in an epithelial cell, it's not probably going to cost you your life right away. It could in a muscle cell, couldn't it? And we already said, especially a cardiac cell. But it could in a skeletal muscle cell. What if you're trying to run away from a predator, or avoid a car, or something of that nature. Well, then running on ATP is going to cost you your life, isn't it? So evolutionarily, we've been selecting as a species, and other species as well, a long time for these mechanisms we're talking about here. A long time. But we're not going to have, right? This is one of the big four. It's going to have special adaptations for it to suit its needs. And so we're going to talk about those, and we didn't have to talk about them in epithelial or connective because they wouldn't be there, and they wouldn't be necessary. But they better be here. All right? So, again, got to be, how can we keep up with the demand? That's really the question here. So, simple cartoons, because again, it's molecular, it's biochemical, so it's not really, doesn't lend itself to a lot of really fantastic pictures, right? So, 3, here's one, creatine phosphate. So this is a chemical that is very high in your muscle and can go even higher, right? There's variation in this, but creatine phosphate, here's again that phosphate, that important, highly charged, unstable aspect of this molecule. So creatine phosphate is more stable than ATP. That's the take home here. It's more stable. So we could call it a storage. Now it doesn't store it long, right? Doesn't store it long, but that may be enough. Just depends on the situation. All right? When do 15 seconds count? That's the question you want to ask yourself right now. All right? So here's a scenario. If I'm at rest, right, energy in ATP is synthesized. It's synthesized constantly through these mitochondria, and it's used pretty constantly. But if I actually have a lot, or I have the potential to have more ATP than I need for the muscle contraction relaxation, well then I'm going to shift my biochemical process, and I'm going to, right, devote the energy that could have gone into putting the phosphates on the ADP to putting a phosphate on creatine. And that's what we show you here. So in resting muscle, I'm going to build. I'm not going to keep making ATP if I don't need it, because it's just going to fall apart. So ADP. All right? And right then, when I get active, I will activate that enzyme, creatine kinase, to put our phosphate, take it off of this and put it back here. It's a pretty straightforward reaction, honestly, and that's why it's good, because it can happen very fast. It's not a complicated biochemical pathway. All right, so there's our take home, right? So I've got this mechanism, because I said there's 3. So I can make creatine phosphate in muscles, and that's going to keep me going. Not very long, but could keep me going. All right, and then I have, of course, glycolysis or fermentation. So I could, these are 10 steps, glycolysis is 10 steps of a biochemical reaction. So I do keep a constant blood glucose. We all do. So glucose is available, right? And if it's not coming into my blood, I've got, when I had plenty of energy, I made glycogen. That, again, that was a storage when times were plenty for energy. So I can tap into these, freeing up a glucose in the muscle cell. And the muscle cell, right, out in its sarcoplasm, has all these enzymes that allows you to oxidize glucose and produce ATP. Now, the problem with this, again, because there's limits, is that you only get 2 ATP. So this is a really nice simple cartoon. It really takes the take-home, you really get the take-home message. You get 2 ATP. If you can fully oxidize glucose, I can get about 36 ATP. So I'm really taking a loss. It's like, really underselling this really important molecule, glucose. So the potential energy is still wrapped up in this, pyruvate, which I do want to pay attention to, because the real decision here about what I do has to do with how much oxygen I'm getting. So if I'm not getting oxygen, then I just end up with 2 ATP, and I call this glycolysis fermentation. And I'll get lactic acid. Right? There'll be one last chemical conversion. We'll actually reduce pyruvate, and we'll produce lactic acid. If there is oxygen, then great, because then I will actually get 36 ATP. So the question on this slide, the real burning question as we end the class is, so when is it that I don't have oxygen? When I don't breathe? Well, yeah, that's an obvious one, right? So, but let's face it, even if you stop breathing voluntarily and you stop it, right? Because you can choose to hold your breath, can't you? You will pass out from the changes, physiological changes in the body, and you'll start breathing again. So that's not really the problem here, is it? The problem is one of delivery. As I made the comment to you, Tanner, about when we have pain in the body, often I say, look, it's probably cardiovascular or neuro. So here's definitely a cardiovascular thing, isn't it? That's the only way to get oxygen around the body. And so all these muscles in here that you're looking at, you got to deliver this oxygen. It only comes in through your lungs, doesn't it? Can you think of any other place that oxygen can come into your body? Because I can't. You might know something I don't, and that's fine. But I don't know of any other place that you can really get oxygen in the body. So it's got to enter in the lungs, and the lungs transfer it to the cardiovascular, don't they? And then the heart pushes it. So do you see where there could be a problem here? Because your heart can only push so often and with so much force. It's limited too as a muscle, isn't it? So is it possible that you might not be able to deliver oxygen fast enough? Because remember that oxygen is being used constantly by these mitochondria. Is it possible that you might not meet your oxygen demand? Yeah, it is, as a matter of fact, right? Different for all of us, but it certainly is. And we just tie it up in this word strenuous activity. So if you're pushing your muscles, running in weightlifting does this, right? You can't get the oxygen there fast enough. You will have to settle because you need the ATP, and you will settle by doing glycolysis. That's your settling. So you will build up lactic acid. And this, of course, is a limit as well, just like we said with creatine phosphate. You probably only have enough glycogen and can only, right, well, it's not even the glycogen itself that's really the problem here. It's that you're just not going to make enough ATP to satisfy the muscle's needs. It's not efficient. And so you'll keep moving maybe for another minute or two. So we bought ourselves a little bit more time, but you won't manage to keep this going. All right? So that's key, right? But this is our second mechanism because we have to have these abilities. And I'll have to leave you hanging on what the third one is. Now you can read ahead. Hopefully you are reading some of this, right? So that you can